Greetings everyone, and welcome to the next video in my lecture series on differential equations. We're still working on Laplace transforms, and in this video we're doing examples of IVPs, or initial value problems, involving translations on the s-axis. So for our example, we're solving y double prime minus 4y prime plus 4y is equal to t cubed e to the 2t, where our initial conditions are y of 0 equals y prime of 0 is equal to 0. So, in order to start our answer, we're first going to take the Laplace transform of both sides. Just going to write that down. And then we're going to apply the initial conditions. So to start off, we're going to take the Laplace transform of y double prime. And as you recall, if you look at a Laplace transforms table, you're going to get s squared capital Y of s minus sy of 0 minus y prime of 0. And that entire term inside the brackets is y double prime. And then we're going to take negative 4, and then the Laplace transform of y prime. So we're going to take Laplace transform of y prime here, and we're going to get s capital Y of s minus y of 0. And that entire term inside the brackets is y prime, and then plus 4 times the Laplace transform of y, which is just capital Y of s. And then we have to take the Laplace transform of the right-hand side. So just to be consistent here, Laplace transform of lowercase y is uppercase y. And please do be really careful of the difference between the capital Y's and the lowercase y's. The capital Y's are the Laplace transform of the function y, and the lowercase y's, y of 0 and y prime of 0, are initial conditions. Okay, so now we're going to take the Laplace transform of the right-hand side. When we do that, we're taking the Laplace transform of t cubed e to the 2t. The t cubed part gives us 3 factorial over what would normally be just an s raised to the 4th power, because it's n factorial over s to the power of n plus 1. And the e to the 2t gives us a shift. Instead of s, we write s minus 2, because our shift is s minus a, where the initial function was raised to was multiplied by e to the at. Okay, so now that we've done that, we're going to also apply our initial conditions. Our initial conditions are here, where y of 0 is equal to y prime of 0 is equal to 0. And that means we're just going to have a bunch of 0 terms. So the y of 0 term goes to 0, the y prime of 0 term goes to 0, and another y of 0 goes to 0. And if we clean this up a little bit, we get that s squared y of s minus 4 sy of s plus 4 y of s is equal to 3 factorial, which is just 6, over s minus 2 to the 4th power. So our next step is going to be to solve for y of s. So that we're going to factor out y of s. We get y of s onto s squared minus 4s plus 4 is equal to 6 over s minus 2 all to the 4th power. And of course, s squared minus 4s plus 4 is equal to s minus 2 squared. Is equal to 6 onto s minus 2 to the 4th power. And then solving for y sub s, we get 6 over s minus 2 to the 6th power. Now, that's all very convenient because we're not going to have to do anything nasty with partial fractions, but it would also be really good if we wrote it in the following way. We're going to have s minus 2 to the 6th on the bottom and a 6 out front. And in order to take the inverse of Laplace transform, it would actually be really handy to have it in the form of 5 factorial. I'm going to try to make that 5 really exaggerated so it doesn't look like an s. So that's a 5 factorial. And to balance things out, I'm going to divide the 6 by 5 factorial so that when the two 5 factorials cancel, giving us what we had to begin with. And the nice thing about the 5 factorial about the s minus 2 to the 6 is that's now in the form of n factorial over s minus a to the n plus 1. So now, to wrap this up, we're going to take the inverse Laplace transform of both sides. And of course, the inverse Laplace transform of capital Y of s is just y of t. And then the inverse Laplace transform of the right-hand side is going to be 6 over 5 factorial times the inverse Laplace transform of 5 factorial over s minus 2 to the 6. The s minus 2 is a shift of 2. That gives us an e to the 2t. And the 5 factorial over some function of s raised, a linear function of s raised to the 6th power is going to give us t to the 5th. And you could leave it like that if you want, or you can multiply out the factorial to get 1/20th e to the 2t times t to the 5. And we're done.